مفيدة للجميع إن شاء الله. فراح أبدأ إن شاء الله ب sharing ال slides. Okay, deep learning in biomedical engineering. بداية إن شاء الله راح أحكي عن deep learning in general, then I'll focus the applications in biomedical engineering. Okay, briefly the outline of this workshop will focus on what is deep learning, what are the applications of deep learning, and mainly what are the applications in biomedical engineering, then what are the types of deep learning, and we'll talk more about convolutional neural network and recurrent neural network and pre-trained neural networks and transfer learning. Actually, all of us know that artificial intelligence is promising and running effectively in healthcare. There are many categories under artificial intelligence, such as machine learning, natural language processing, expert systems, vision, speech, planning, robotics, and we know that neural network is a complex technique in machine learning, while deep learning is the most complex type in machine learning. Okay, that we will focus during this workshop. Now, what is deep learning? Actually, deep learning is a subfield of machine learning that deals with algorithms inspired by the structure of, and function of the brain. And we see here that also machine learning is a subcategory of or subfield of artificial intelligence. Actually, we see that deep learning is the application of machine learning that uses complex algorithms and deep neural nets to train a model, while machine learning focusing on the applications that allow a system to automatically learn and improve from experience, while artificial intelligence, which is the general umbrella, has the ability of a machine to imitate or mimic intelligent human behavior. Now, if you want to compare between machine learning and deep learning, the main difference is actually when we talk about classical machine learning or machine learning in general, we should have inputs, and there should be an expert domain that extract the features from the input for a certain problem. Then these features should be applied to certain classifiers to predict certain output. While on the other hand, if we see deep learning, we have no feature engineering. That's actually we apply input for a certain problem, and that input is propagated through several layers of neural networks. At the end, the prediction will be based on automatically extracting of the important features. Simply, we can describe this point if we consider we have input data. Okay, just to take the laser pointer. Okay, here, input data in traditional learning algorithms, that's machine learning, we should have the block of feature engineering. Okay, and actually this step takes lots of time and it's expensive in terms of time. While in deep learning, directly we have input data to deep learning. There's no further feature engineering. Assuming the traditional learning algorithm is a black box regardless of the type of classifier, and deep learning is a black box regarding the type of that deep learning. So the main difference is there's no feature engineering in deep learning. Now, if we can define deep learning as a method of machine learning, as we just said, running over artificial neural networks that uses multiple layers to extract higher level features from large amounts of raw data. Also, deep learning methods apply levels of learning to transform data into more abstract and composite information, which means we in deep learning focus on the most important features to be extracted at the end, using several layers of neural networks, as we will discuss later. And deep learning has been rapidly developed in recent years in terms of both methodological constructs and practical applications. And we'll see that the revolution in technology, okay, and the right amount of data and the development in practical applications in terms of algorithms, all of these points actually have an important effect on the deep learning as a field. Now, what are the main advantages or main characteristics or aspects of deep learning over machine learning? We can summarize them besides the point that we have just pointed out, which is regarding the feature extraction. Regarding it process huge amount of data. Actually, machine learning algorithms work with a huge amount of structured data, but deep learning algorithms can work with enormous amount of structured and unstructured. When we say structured, which means we have input and output. Okay, we know that's called as labeled. Okay, data. This is a main advantage of deep learning over machine learning. Also, perform complex algorithms. But machine learning algorithms cannot perform complex operations, while when we say deep learning, then it can apply complex operations. That's in terms of when we say as an algorithm. Okay, if we compare between the algorithms, then most of machine learning algorithms are simpler than deep learning. Also, to achieve the best performance with large amount of data. If we apply the same input for both of machine learning and deep learning, most of problems have achieved better performance in terms of deep learning compared to machine learning. That is, as the amount of data increases, the performance of machine learning algorithms decreases. So to make sure the performance of a model is good, we need deep learning. And as we have just said, due to the revolution in data size and in the complexity of algorithms, then machine learning outperforms, deep learning outperforms machine learning. And the last point regarding feature extraction, as we have just pointed out, machine learning algorithms extract patterns based on labeled sample data, while deep learning algorithms take large volume of data as input and automatically extract features during the neural network layers. Okay. So now we have just so far defined deep learning in general. Now, what are the applications of deep learning? The general applications of deep learning, most of us use several applications, and they are actually based on deep learning. For example, in image recognition, that can define, deep learning can define certain objects or features in a certain image. Speech recognition, deep learning help to recognize certain speech and natural language processing. Also, deep learning can help to recognize certain text. Machine translation, all of us, I think, used Google Translator, which is actually based on deep learning, in which the deep learning can almost translate most of word language. And regarding targeting as an application, means that deep learning can figure out what we need. For example, we see here that prediction of your buying patterns. Okay, so Google Translate, prediction of your buying patterns, recognizing the images on camera that are related to certain persons. All of these applications are based on deep learning. Now, if we focus on biomedical engineering, actually there are many deep learning applications in biomedical engineering that has a goal to mainly for early prediction of the diseases. For example, we have medical image processing, diagnosis for diseases, especially the early detection of diseases, tumor prediction, protein structure prediction, drug discovery, as well as material design. And there's many studies in the literature that are based on deep learning related to biomedical engineering. Now, in medical imaging, actually, most of the radiologists make use of deep learning to support their decisions in certain diagnoses. And there are many categories in medical imaging that make use of deep learning, such as diagnosis for making certain decisions, or monitoring of images, generation, such as acquisition, reconstruction, or artifact correction for certain, such as augmentation, okay, that's based on deep learning, and analysis, including segmentation, feature extraction, and transfer, okay, tools. All of these, okay, started from dealing with images from the beginning until the passing through analysis and the final decision of diagnosis or making a decision for certain treatment later on. Okay, these are just images showing some studies that are based on deep learning. For example, diabetic eye diagnosis, okay, skin cancer diagnosis, image segmentation, optical coherence tomography, chest X-ray, image registration. All of these and okay, many others, okay, are based on deep learning, and they resulted in better performance, okay, using deep learning compared to machine learning and other algorithms that are less accurate in giving prediction. Okay, now what's a neural network? Actually, deep learning is based on neural network. So firstly, we need to understand or to know what is a neural network. Simply, artificial neural network is based on the intuition of biological neurons, the human thinking. Here, just okay, need to compare between the biological neuron, okay, that consists of dendrites, cell neurons, axon, and synapse, and see what's the corresponding, okay, elements of these elements in biological neuron compared to the artificial neuron. Here we have the dendrites that corresponds to the input. Okay, this is artificial neuron. We have certain inputs. Okay, we have the connections or the signals, including weights. Okay, and we have this is the neuron, and we have the output. So the dendrites here in the biological neuron corresponds to the inputs in the artificial neuron. The cell nucleus, okay, corresponds to the node, since the processing units in artificial neuron are nodes. And we have the synapse here represents the weights, okay? And finally, we have the axon that is correspond to the output in artificial neuron, okay? Now, as we have just said, deep learning basics is rely on artificial neural network. Now, the artificial neuron, this is a multiple layer of neurons, neural network. We have inputs here, and we have the nodes here, and we have the output layer. Actually, we have three layers: input layer, hidden layer, and output layer. In the input layer, okay, we have the weights that connect the input to the node, and here we have the activation function. Actually, in the hidden layer, the weighted the summation of the weighted inputs, okay, is applied to the nodes. Then it will be activated, and the output will be fired based on the activation function. Okay, so the artificial neuron was inspired by, as we have said, human neurons, which are the nerve cells that make up our brain and central nervous system, and are largely responsible for our cognitive abilities. And deep learning refers to the artificial neural network with more than one layer of neurons. Actually, we have in machine learning artificial neural network. it consists of multiple layers of network, while when we say deep learning, okay, actually it's more complex than artificial network in terms of the number of layers. Okay. Now, okay, the main two steps in neural network, actually we need, assume we have here we have inputs, okay, and we need to calculate the weighted sum of the inputs and add a bias. Okay, remember that when we say inputs here in machine learning represents features, while in deep learning the inputs represents the data, the input data as is, okay, as a feature, as a text or image or audio, whatever, okay. While in machine learning we have the features. Now, we need to pass the calculated weighted sum. That is, each input is multiplied by the corresponding weight on the channel, on the connection, and then we will apply summation of the weighted inputs, okay, and sometimes add to a certain bias, and this is represents a transfer function within the node. Then there should be applied an activation function. Okay, certain now we will see that we have different activation functions to be applied to the transfer function. That activation function resulted in a fire to certain outputs. Okay, and sometimes here we have unfold the transfer and activation, and usually these two steps within the one neuron. Okay, these are two steps represents just one, okay, neuron. Now, okay, we have activation functions. We have different types of activation functions, such as sigmoid function here. Okay, we have threshold function, we have the hyperbolic function, and we have the rectified linear unit function. Okay, sigmoid function here, okay, in this shape, when we say 5x equal 1 over 1 plus exponential minus x, and x here represents the, okay, the weighted sum. When we apply the weighted sum, okay, to the activation function, then it will be fair to certain, okay, output. Okay. For example, for threshold function, the activation function will result in 1 if x is greater than or equal 0, and 0 if it is less than 0. Okay, and in hyperbolic, this is the activation function, and in ReLo, the maximum, okay, x, any value greater than 0, it will be linearly proportional to the input. Okay. Now, so far we have known the structure of neural network in terms of the input, the activation function, the output, the hidden layer. Now, what is the working principle of a neural network? Okay, actually we have mainly two steps for learning process. When we say learning, that is the neuron, okay, similar to the human neurons will learn during, okay, over certain inputs. Now we have here mainly two steps: forward propagation and backward propagation. Forward propagation represented, okay, forward, okay, and backward in the backward side. Forward propagation simply as, okay, we just said it is the weighted sum of the inputs activated, okay, then the outputs will be compared, okay, with the actual outputs, okay, using the mean square error, okay, that is the y hat here represents the model output or the predicted output, and this is the actual output, and they will be compared to get the cost function, or which is simply an error, okay, which is the difference between the predicted and the actual. This is, okay, during forward propagation. The backward propagation is an important step to optimize or tune the performance of the neuron, okay, or the network simply. Now, if the error is greater than the certain limit or our threshold, then the cost function will be back propagated, okay, to the neural network, and to update the weights and bias, that is the parameters that should be updated, okay, during back propagation, in order to optimize or tune the cost function to get the most accurate output. Okay, now we'll see how neural network predict certain input. Again, imagine that we have here input layer, and this is the output layer, and we have a hidden layer consist of two layer of neurons. Here we have inputs, and the connection represents the weights. So, this is just as animation of the neural network work. The first step is applying the weights to each interconnection. Okay. And usually you can ask, how can we determine the weights? Okay. Usually the weights are applied randomly, and then they will be adjusted iteratively during the back propagation step. Next, after applying the weight and weighted sum, then we will apply the activation function to the hidden layers to decide which nodes to fire and carry out feature extraction. That is, when we apply the activation function, then the output will fire to certain limit to get the predicted output. Now, applying the cost function to minimize, okay, the difference between the predicted and the actual, okay, using algorithm called gradient descent algorithm, which is an algorithm used to find the cost function and optimize it during learning process. Now we have finished the forward propagation, that is weighted sum, activation, find the predicted output, and find the cost function. Then, okay, the cost function will back propagated, okay, back over the hidden layers, back to the inputs, okay, to improve the model. Now, applying the updated after the weights are updated, okay, after the back propagation, and then the updated weights here, these are the updated weights, will be applied again to the neural network, and forward propagation will start again, okay, as the first step to calculate the output, okay, and find the cost function. And this forward and backward, okay, steps will be applied iteratively over the network until we get the minimum cost function. At the end, okay, assuming we reach the desired cost function, then the desired error, okay, as a result of the cost function, then we can classify the image based on the extracted features. Okay, assuming we have here a neural network based on deep learning, that is, the applied are inputs and the features are extracted within the neural network. Now, why are deep neural networks hard to train? Okay, actually, artificial network was applied as we have said part of machine learning, and then applied as for deep learning. But until 2006, there was no proper method to accurately train deep neural networks due to a basic problem with the training process. Okay, and the training process mainly lead to a problem called the vanishing gradients. Okay, now. And we said that gradient is the rate at which the cost changes with respect to weight and bias. Okay. Now, the problem is that since we have a huge amount of data and we have multiple layers in the deep neural network, then the researchers found that if they, for example, draw a graph represents the change of weights over iterations, if the weights kept constant, then there's a problem called vanishing gradient. That is, the weight doesn't updated during iterations. So this is was one reason. Okay, based on it, there should be research to update the training of deep neural networks. Actually, the vanishing gradient problem occurs when the gradients of the loss function with respect to the weights, okay, in the early layers become vanishing, okay, small. And as a result, the early layers receive little or no updated weight information during backward propagation, leading to slow convergence or even stagnation. That is, the learning stuck on certain values, okay, and doesn't update it during the process of training process. Okay, simply we can here, okay, in this slide shows how the gradient process occurs, okay? Okay, now let's understand gradient like a slope, okay, here, and the turning process like rolling a ball. Assuming that the slope is not sharp here, okay, then the ball will rolling slower than if the slope is faster. And okay, and actually the researchers found that they can imitate this, okay, scenario to activation functions. Okay, this is just the gradient descent idea, okay, which is an optimization of algorithm for finding the minimum of a function here. Okay, so this is the when you say gradient descent, that is, we need to find the local minimum, okay, or the lowest error, okay, during the training process. Now, referring back to the punching problem, actually, we just said that we have basically three types of skills that drive a deep learning process. Okay, they are the data. Okay, we know that now during the revolution and the rise size and complexity of data, and we have computational time. Now we see we have GPUs and cloud computing. All of this, okay, have important development in deep learning and algorithms. There are a lot of algorithms that have been developed, okay, in deep learning to let it more powerful than before. Now, the researchers, okay, focus on these three terms, okay, data, computation time, and algorithms, and they look at computation time in order to improve or to avoid the vanishing problem. So to improve the computation time of a particular network, they look at the activation function, okay, that plays an important role in the speed of the learning process. So if you look at the sigmoid, okay, function is used here, okay, then graph appears as shown here. Okay, this is the function of sigmoid. We see that the value of slope or the gradient of this function at the extreme ends, okay, is always close to zero. Therefore, the parameters are updated in a very slow manner, okay, resulting in a very slow learning. Okay, assuming here we have a ball and it's okay rolling over this. Okay, so the researcher found that okay, it roll in slower manner. Okay, so that leads to sometimes if we apply the sigmoid function, okay, to deep learning, then we will result in either stagnation, okay, stuck in a certain error, okay, and the weights will not be updated, okay, or the convergence will take too many time. So the idea was to exchange the sigmoid function to a new function called rectified linear unit, okay, which is one of the biggest progress in neural networks. Okay, this is the ReLO, okay, and it's updated the parameters much faster when the value of the slope is 1. Okay, so any value greater than 0 will be resulted in corresponding output to the same value. So this is the dominant reason for faster computation of the models. And if we look at the literature and the research studies that based on deep learning, most of them based on rectified linear unit as an activation function instead of sigmoid function that was used, okay, previously. So actually, okay, we can summarize this point that rectified linear unit addresses the vanishing gradient problem. So we avoid this problem, actually, and improve the convergence speed and accuracy of the deep neural networks. and has computational advantages. Okay. Now, what are the types of deep learning networks? Actually, there are many types of deep learning neural networks. We have convolutional neural network, we have recurrent neural network, long short-term memory networks. Actually, the CNN usually applied for images, recurrent neural network, and long short-term memory networks. And when we say in biomedical engineering, they apply to sequence of data such as molecular sequences, DNA. Okay. Recursive neural network. Also, we have extreme learning machine, stacked autoencoders, and generative deep learning. They are the most recent, okay, types of deep learning, and all of them have different applications regarding biomedical engineering with good performance. Okay, again, just okay, to compare between CNN and deep learning model. Okay, simply, okay, the learning process is in backwards, okay, and forward propagation occurs. We have, for example, one hidden layer or two. We have few hidden layers in neural network, while in deep learning model, okay, we have, okay, learning and generalization. Okay, and we'll see what is the meaning of generalization in deep learning model. We have multiple, okay, layers of hidden layers, and they can reconstruct the error, okay, um, 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 uh, in a term, okay, that outperforms the simple artificial neural network. And the idea of generalization actually resides in that not all of the input image will pass as is to the output. There will be some kind of subsampling or reducing the size of the input, okay, and focusing on the extracted features and the important features in deep learning. So the generalization will occur, and okay, in this way, and to avoid overfitting or the vanishing problem. So a convolutional network can be defined as a regularized type of feed-forward neural network that learns features by itself via filter or kernel optimization. Now, what is the meaning of regularized type? Regularized type means that the CNN will reduce overfitting, okay, the vanishing problem by focusing on the important features during feed-forward neural network that learns features and extract features automatically by itself via filter or kernel optimization. Now, the filter here represent, since we talk about images, okay, not certain features, then the weights will be implemented in filter, okay, or kernel. So the weights that are applied to the connections in the CNN, okay, are presented as filter or kernel. Now, CNNs are specifically suitable for images as inputs, as we have just said, and kernel, which is a filter that is used to extract features from the image. And the network learns to optimize the filters through automated learning, okay? Since we don't have features, as we have just said, we have the image as is will be applied, and the filter will apply to the image to extract the important features. So the main steps of CNN are the following. We have the first step, actually comprised of consists of two steps: are convolution and activation. Then we have pooling, and then we have flattening, okay, before the predicting the required output. Okay, so actually we have three steps: convolution, pooling, and flattening. And convolution included implicitly the activation step. Okay, this figure shows the convolutional network. We have here input image. I think there's problem in speed, so okay. Okay, we have input image here. Iteratively will be applied convolution, subsampling, which is the pooling, then convolution, subsampling, till we reach the last step, which is the flattening to get the fully connected layer. in convolutional step, okay, actually we will apply a filter to a subregion of the image here, okay, and the resulted will be feature maps. The feature maps represents the weighted, okay, regions of the inputs, and we have more than one feature map, as we see here, because we apply more than one filter, okay, at the same time for the input. Then we have subsampling, which represents pooling, that is, we need to reduce the size of the feature map using different types of pooling. We might apply either max pooling or average pooling. And then we'll apply convolution again, then subsampling, okay, and we'll see now in deep, okay, what is the meaning of each step here, okay, just we need to imagine, okay, in this figure that we have the learning, okay, step of the features or the exacting features of the in CNN will be applied from the beginning until this step, okay, and finally after the getting the flattening or fully connected layer, we'll apply the prediction, okay, step. Now, regarding the convolution layer or the first step, okay, we have the input image here. Okay, this is 5 by 5 image, and you know when the cell, each cell of the image represent pixel value, and we have here the kernel or the filter. We have here 3 by 3 kernel that will be applied to subregion of the image. Okay, and it will be slides stride by, okay, and from left to right, then from top to bottom until the entire image, okay, will be covered by this kernel. Actually, what happens here? Okay, now each value of the kernel, which is the weight, okay, and again, the kernel represents the weights, okay, that apply to the image. We have here 1 will be multiplied by 5, then 0 by 8, and 1 by 3, and we will go, okay, in this equation, okay, 5 by 1, 8. So every weight in the kernel will be multiplied by the pixel value until we cover the 3 by 3 region, subregion of the image to get a value that corresponds to the convoluted output, which is the feature map. Okay, and similarly, then this kernel will be, okay, just is the pen. Then we'll stride, okay, once again from this to this to cover this region. Okay, and again when we multiply 1 by 8, then 0 by 3, 1 by 9, and similarly to cover this subregion, and the resulted value will be put it here. Okay, next, okay, and we apply this region, okay, and the value will be here, and similarly we will go from top to bottom to cover all the pixels of the input image. Okay, yes, what I have just explained is here, okay? So the kernel will be moved stride. Okay, when we say stride, the concept of stride presents the jump of the kernel over the pixels of the image. So here, when we say 1, so it was here, then it will jump 1 stride, this one, then 1 stride to this one. So the stride presents the movement of the kernel, okay, for each step, okay, 1 pixel each time. Then the next step, okay, assuming now, okay, assuming here we applied activation, sorry, okay, assuming at the end, okay, when the resulted convoluted output, which is the feature map, will be applied to activation function, okay. Then we apply pooling. Pooling or subsampling is required to downsample the detection features in feature maps, okay. Now, what do we mean by sampling or pooling? Actually, we have 2 types of pooling, max pooling and average pooling. It involves sliding a window. For example, when we say that the subsampling needs to be 2 by 2, then it involves sliding a window of 2 by 2 across the input data similar to that happens in the convolution step, but instead of performing matrix multiplication, okay, we applied either max or average. For example, here, if we apply 2 by 2 matrix to this region, okay, so the maximum value here is 6. Then we'll put it in the output of the pooling step. Then what is the maximum in this region will be 8. The maximum of this, okay, so the window will be slides from, again, from left to right and from top to bottom until covering the feature map, okay, to get a reduced size of a matrix to present the result of pooling. In case of averaging, okay, or average pooling, then we'll take the average of these values and put it here, and similarly we'll apply this to all the feature map. So pooling serves the dual purposes of reducing the spatial dimensions of feature maps and controlling overfitting. Okay, so pooling is has an advantage in reducing the size and constraint on the important features. And remember that we have more than one filter that apply to the input image. So we'll have more than, okay, one feature map, and at the end, more than one, okay, output of the pooling step. The last step is image flattening. Actually, image flattening is converting the multidimensional matrix, that is the result of pooling here. Okay, this is the result of pooling will be applied to the flattening, that is converted to one-dimensional matrix. Okay, the 2 by 2 will be 4 by 1. So in pooling layer, since we have more than, okay, one feature map, and then we'll have more than, okay, one output in the pooling layer, then all of these matrices will be converted to single continuous vector, okay, in this way. So this is the first, okay, matrix will be here, then the next matrix will be here. So all of these multiple, okay, matrices in the pooling layer will be converted to one single long one-dimensional vector, okay, in the flattening. Now, what is the goal or the purpose of flattening actually? Actually, the saving process of JPG or any type of image or transferring occurs in the flattening form, okay? And usually the prediction process in neural network happens in one dimensional vector. Okay, now I'll move to showing you an animation of the CNN. Okay. So this is, sorry. I need to lock the camera, so, okay. Is this now? Problem in the this one. Okay, now I'll share. I don't think it's screen.
دكتورة بس ما في صوت. دكتورة لينا إذا سمعتنا
يس،
الصوت
أنا سامعة.
الفيديو مش واضح.
آه، أوكي. مش عارفة. اوكي. um, I think الصوت ما كان واصل، سمعت منكم بس انه على الاقل كان في translation. اوكي. لا طيب. back to the slides. ما كان واصل صوت الفيديو صح؟ سامعيني؟
إيه دكتورة ما كان.
اوكي، انا توقعت هيك، بس انه يعني الكويس انه كان في ترانزليشن اللي بيحكوا موجود يعني. اوكي، فيعني انه الكونتنت اللي بدي اوصلها، اوكي اتوقع انه وصلت يعني للطلاب او للحضور. طيب. بدي اطلب منكم هلا، لو في اطلب منكم تعملوا كويز صغير، يعني سؤال تجاوبوا لي عليه. رح احط لكم اياه على الشات وعلى اوكي، على الواتساب. اوكي. ستوب شيرينج. اوكي. في مشكلة أحس. ستوب شيرينج. بدي أبعث لكم هلا سؤال. اوكي. I hope انه تجاوبوا عليه. تبعثوا على ال شات هون. تبعثوا على الواتساب كمان. سامعيني؟
دكتورة صوتك مسموع.
تمام. اوكي خلاص. اوكي، فكرت مشكلة من عندي يعني.
أنت كنت تحكي قبل شوي، لأن
لا
آخر
حكيت،
إشي
لا.
سمعناه إنك
لا
بدك
بس انه
تبعتي
لا,
على
لا ما حكيت شيء
الشات
بس.
وعلى
بس.
الواتساب.
اوكي.
دكتورة حددي لهم كم معهم دقيقة.
بس يعني بس 1 minute. اوكي هلا يعني ارجع الريسبونسز واشوف.
تمام مهندسين، الكوز عندكم هنا بالشات تيمز وعلى الواتساب. يا ريت تتعبوه، هو سؤال واحد يعني.
بس يس اهو. اوكي.
بس دكتورة، في المهندسة سارة عندها سؤال إذا
اتفضلي. انا
بيصير.
مش شايف حدا رافع ايده حدا. اوكي تفضلي، اللي يسأل انا مش شايف بصراحة. اوكي.
تفضلي سارة، المايك مفتوح عندك.
سلام سليمان. يس اها. لا المايك عندها مش مفتوح، المايك كأنه.
السلام عليكم.
عليكم السلام.
بنستفسر منك على الأكتيفيشن فانكشن.
مم.
في أي حالة مثلا نستعمل السيجمويد وأمتى نستعمل الريليو مثلا؟
أوكي.
هل في يفرق يعني في الكود ولا عادي نستعمل أي واحد؟
لا هو بيفرق، اكيد بيفرق. اوكي، هلا فعليا السيجمويد اتس ابليكابل في حاله يعني بالماشين ليرنينج. اوكي، sometimes اتس ابليكابل. هلا يوجوالي يعتبر الاكتيفيشن فانكشن هو هايبر بارامتر. اوكي، انت كديزاينر المفروض تعدله. هلا مع مستوى الديب ليرنينج حكينا انه يعني لحد 2006 وجدوا انه كانوا يستخدموا السيجمويد مثلا، وجدوا انه لا في مشكله، انه يعني بيعمل لنا مشكله انه ما بعمل ابديتد للويتس. اوكي، اوفر الاتريشن مثلا. الايرور بيكون دائما عندنا عالي مثلا. اوكي، ففي عندنا بروبلمز وعندنا بكون كمان كبروسيس كومبيوتيشنال تايم كثير بطيء في التريننج. اوكي، فمشان هيك وجدوا مثلا الريلو. فانه هلا فعليا الريلو هو فعليا يعني الدومينانت اوكي از اكتيفيشن فانكشن في الديب ليرنينج. اوكي، الاستجمويد سم تايم ابلايد اذا بنحكي عن مستوى مثلا ماشين ليرنينج، بعض التكنيكس بيكون مش هالفرق، مثلا اذا كان عندك حجم داتا قليل او اوكي سمبل بروبلم. لكن اذا بتحكي عن كومبلكس بروبلم وهيوج داتا، الريلو اوكي يعتبر يعني اوت بيرفورمز. اوكي.
تمام، شكرا.
عفوا. في سؤال انه اوكي شخص بيحكي انا PhD researcher in computer science. I want to know what are the latest AI techniques used in brain tumor accurate diagnosis and detection. اوكي اكشولي هلا حكينا احنا في شغله على مستوى الديب ليرنينج، في هلا الجنريتيف ديب ليرنينج، وفي عندنا الانكودر. فهذول التكنيكس تعتبر شويه recent اوكي types of deep learning that can be applied اوكي بطريقه عنا more powerful than ممكن حتى CNN. اوكي. اوكي لا انا لسه مش عامل شير، هلا انا بدي اعمل لكم شيرنج للريسبونسز بصراحه. اوكي. أم أم واضح الشير للريسبونسز لكم؟
دكتورة واضحة.
ان يس الانسرز كان انه الأغلبية جاوبين إنه information passed between the network layers. هلا نحكي إحنا activation. what's an activation؟ أوكي، هلا في ناس جاوبين إنه weights of convolution layer. الويتس هم لا هم فعليا هم الفاليوز بيكونوا بالكيرنل. أوكي، within the kernel. so لا. أوكي، الفلترز of an active a convolution layer. الفلترز لا، الفلترز هم فعليا هم similar للويتس لكن as a matrices. أوكي، هلا information passed between the network layers. شو الانفورميشن هي باس بتوين ذا نتورك لايرز فعليا؟ شو هي الانفورميشن اللي بتكون باس بصراحه؟ امم ايش بصير propagation بتوين النتورك سواء فورورد او باكورد؟ ايش الانفورميشن هي فعليا؟ عباره عن ال الداتا. اوكي، معمولها ويتنج ومعمولها اكتيفيشن ماشي. لكن انا سؤالي وات از ان اكتيفيشن؟ جواب صحيح هو بصراحه none of the above. اوكي، 10 نجاوب عدد قليل جدا. الاكتيفيشن هو الفانكشن. اوكي، سواء عندك شو يعني هو كفانكشن. اوكي، فعليا الموجودين هون انا بس انه يعني you should recognize الكونسبتس اوكي اللي ذكرناهم في البدايه، انه نعرف شو يعني input، شو يعني hidden layer، شو يعني output، شو عندنا الويتس ايش هم. اوكي، لما نحكي الفلتر هو عباره عن فعليا هو weights. اوكي cells of weights. information passed between the network layers information بس مش activation. اوكي، بتكون يا activated يا اوكي. لكن كلمه activation implies the function okay that's applied to the data to be fired to certain limits. Okay. طيب. Okay, I'll refer back to the slides. Stop sharing here. Okay. Um, Now, for mathematical understanding of the convolution neural network, okay, actually now we describe the steps, okay. We have convolution, we have activation, we have pooling, and we have flattening, okay. Now, assuming we have an image of n by n size, and the filter is f by f. In the previous example, we see that the image was 5 by 5 and the filter was 3 by 3, okay, if you remember. And we have P as padding, okay, and I don't know if you know what is padding or not, okay. Padding actually is a step that sometimes applied to the input image to avoid the problem of the border of the image, to avoid losing information of the image. For example, if we have, I refer back, okay, just to explain this point. For example, for this image, okay, how can we apply padding for this image actually? We add cells, okay, in the border. Sorry, البين مش مساعدني هون بالتيمز. Okay, كون filled by 0. Okay, this is for the border كامل. Okay. Okay. Now, okay, all of these are zeros here. Okay, the cells. So here we have 0. Okay, and all of these are okay 0. So in this way, padding, the idea of this step is to avoid losing information, because when you apply, you see here, the kernel here, okay, the border of the original image, okay, are considered just one time, okay. So in this way, there will not be focusing on the, if there is important features on the border, then there will be lost by, okay, steps. So to avoid this, okay, we apply padding to allow the borders to consider more than one time when you apply the kernel, okay? So you have here zeros. So the this is the concept of padding. Okay, stride step. We say the stride that when we move the kernel, okay, from left to right, we move just, for example, 1 pixel, okay, each time. So this is the SS. Now the dimension of the output will be what? Okay, the dimension of the image, which is n plus 2p minus the filter size or the kernel size divided by the stride value, and this is plus 1. So this is for the, for example, the height, and this is for the width, okay, of the output. And I'll consider this example to show this, okay. Assume we have this, okay, image and input, and this is the height and width of this image, 39 by 39 by 3, which is the number of channels. If we have RGB image, okay, red, green, blue, then it will have number of channels equal 3, and if it is in a grayscale, then this value will be 1, okay, because just we're looking at the brightness in the grayscale. So now this is the image, and we have 39 by 39 pixels. So this is the height and the width equal 39. The number of channels equal 3. Now, if we apply a filter size of 3 by 3, this is the F will be 3. Stride will be 1. That is, we move the filter just 1 stride each time, and the padding is 0. That is, we no padding, okay, in this image, and we apply 10 filters, okay, or 10 kernels for, okay, this image. Then what will be the size of the output actually, okay, in the convolution step? This is the equation here, okay. It will be n plus 2p minus f over stride plus 1. This is what I have just mentioned here, okay, n plus 2p minus f over s plus 1. This is for the height, and this is for the width, for example. Now, here we have n equal 39 plus 2p. We have no padding. This is 0, minus f, which is the filter size, which is 3, divided by s stride is 1, plus 1, and the value will be 37. Okay, now this is the output. The height, width equal 37. The number of channels equal 10, which is the number of filters. Since we applied 10 filters, then we'll have, okay, 10, which is in this where, for example, as the number of feature maps, okay? Then if we apply conversion again, we'll, for example, apply the filter of size 5 and the stride, now it's 2, not 1. Okay, in this way, when we say the stride is 2, then we will jump 2 pixels, okay, in the next kernel applied, and padding is 0, and we have 20 filters. Okay, in this way, if we apply this equation to these values, then we will have 17 by 17 by 20. Similarly, again, till we reach the final, okay, step, and then now we'll talk about flattening, okay, which is converting the two-dimensional to, okay, one single vector, okay, and then to apply it for softmax, or to get, for example, this activation function to get the predicted output. And just okay to know, usually in deep learning, an activation function called softmax is applied at the output level. It deals with multi-class, okay, output. When we say, for example, sigmoid is applied if we have a binary, okay, or just 2 classes, for example, and softmax is applied for multi-class, okay, values. Okay, I hope, okay, it's understandable now regarding the mathematical understanding of convolutional network, getting the size, okay, of the matrices. Any question regarding CNN? Okay. سؤال إنه okay, it is the output of layer after, is it the output of layer after the function? Which function do you mean? لين الحلمان تسأل. After the function, which function? We have activation function, okay, over the network layers, okay, and at the end we have, okay, activation function. So each, okay, step of convolution, okay, بكون بعدها فيها activation function. طيب. Now, regarding recurrent neural networks, actually, recurrent is a type of artificial neural network designed for sequential data processing. And when you talk about biomedical engineering, there are many examples regarding sequential data processing, such as molecular, okay, problems dealing with genomics and proteomics. We have a sequence of DNA dealing with, for example, text, okay, مثلا في عندنا بعض electronic health records, okay, they need to apply neural network or deep learning to recognize some paragraphs, okay, of text. So sometimes the recurrent neural network is applicable. Why? Because, as I don't know if you remember in the video that you have just seen, they talk about recurrent, and there's a loop, okay, in the hidden layer to remember the output, okay, of hidden layer for a while. So unlike traditional feed-forward neural networks, okay, the recurrent neural networks have connections that allow information to flow in a loop, okay, enabling them to maintain internal memory of past inputs, okay, and this is an advantage when you talk about sequences and long sequences to avoid forgetting some information, okay, during the neural network. And for example, if you apply, for example, the sequential data processing over CNN, okay, we will stuck in stagnation problem, okay, which is the problem that we said in the beginning, the vanishing problem, okay, because no remembering of the data because they are long, okay, so might no convergence or no update for weights. So the idea is to use recurrent neural network. So this memory-like property makes RNNs particularly useful for tasks that involve sequential or time-dependent data. Actually, in healthcare, RNN is used for the diagnosis of disease, while specific forms of recurrence also applied to improve the quality of medical imaging sometimes, okay? Usually when we take photos or images for follow-up process for certain patients and over time, so RNN is more powerful than CNN. Okay, in RNN, it uses hidden layer that remembers specific information about a sequence, okay? So anyone can, sometimes some persons, they have confusion with recurrent and backpropagation, okay? What's the difference between recurrent and backpropagation? Any idea؟ حد حابب يحكي؟ What is the difference؟
المايك مفتوحة للكل، فأي حدا حابب يشارك بس يفتح المايك على طول يحكي.
Any idea? Recurrent, neural network, and backpropagation. What is the main difference?
دكتورة، ممكن إنه بالريكرنت نيورال نتورك ما إلها علاقة بالويت أو بحساب الويت أو بأدجستمنت للويت، إنه بينما
Yes. Exactly.
بينما بالباك بروباجيشن إحنا عشان نحصل نلعب يعني نغير بالويت حتى يكون الأوتبوت قريب من اللي بدنا إياه.
اوكي تمام جود. يا اسمك بس مش عندي. ربا. اوكي شكرا يا ربا. صحيح. اوكي when we say recurrent, okay, then we say we have a loop within the hidden layer itself, okay, but in backpropagation then the backpropagation from the output to the input, okay, while here no. Okay, highlight الأفضل. okay. Okay, so again backpropagation is used for learning, while recurrent is just as a for memory purpose, okay? Right. So use, okay, hidden limit to remember specific information about a sequence and has a memory that stores all information about the calculations, okay? And need to inform about the previous inputs before evaluating the results. Okay, here we have unfolding for the we have input and output, and we have the hidden layer here, and this is the loop, okay, as a memory. So we see that the output of the hidden layer, okay, return back to the hidden layer, okay, to be used for the next time. Okay, so here the unfolding in terms of time. This is for the first time, this is for the next time, and this is for the next. So the output of each hidden layer, okay, is returned back to be used for the next time. Okay, so this is will be as a memory to remember a long sequence of data and processing of it. Now, why RNNs? Actually, we can decide to choose either RNN or CNN based on the application, and if we consider the differences, then we can decide, okay, what type of neural network to be applied, okay, on which problem solving. So CNN extract features from spatial data such as image or video, while RNN process sequential data such as text or speech. Okay. Based on this, you can recognize that when you say text or speech, for example, or such as molecular series, okay, then they are long, okay, and they need memory, okay, to be remembered, okay, during the processing step of a neural network. CNN also takes fixed size of inputs and generate fixed size of outputs, while RNN can handle arbitrary input-output lengths. Also, CNN uses shared weights and biases across different parts of the input. Okay, as we just see, so we have kernels of weights, okay, and applied to different parts of the input. When I'm convolution, okay, same kernel applied to different subregions of the image, which reduces the number of parameters and improve generalization. On the other hand, when we see RNN, it uses the same weights and bases across different time steps. The difference is we applied it to different time steps, which allows it to store and reuse information from previous inputs. Okay. I think I have just talk about this. RNNs have gained prominence due to their ability to process sequential data, making them particularly suited for time series medical data and sequential image analysis. While CNN is applied to spatial data analysis, yes, we have just said as video or images. Okay, RNN is based on temporal dependencies, which are crucial for progression of diseases and predicting future health outcomes. So sometimes when we see, we need to apply, for example, preventive diseases, okay, or by predicting future health outcomes, then RNN is more suitable than CNN, and RNN are useful in diagnosing conditions that involve change over time, such as cardiac arrhythmias, neurological disorders, and the monitoring of disease progression through multiple imaging sessions. Okay? So based on the problem we need to solve, we can choose the appropriate deep neural network type. Okay, this is another type of neural network, which is long short-term memory. Actually, somehow it's similar to the RNN. It's a kind of RNN, but it's more sophisticated and capable of learning long, term dependencies. LSTM networks can selectively remember or forget information. So sometimes you can ignore, some remember data, and keep others, and are capable of learn thousands time steps by structures called cell states and 3 gates. Actually, we have input, output, and we have forget gates. Okay, since you are dealing with applying thousands, of time steps. So sometimes we need to forget some processing data by the forgetting gate, and each cell remembers the desired values over arbitrary time intervals. Then they can be, so here we can see the RNN have input, output, just one loop, as memory, while in LSTM we have working memory, the same as RNN, besides to long-term memory, okay? This is simply the idea. I will not go in deep, it's long short term, because actually it's more complex and actually it needs lecture, alone. Now, the last topic, I need to focus is the pre-trained neural network. Pre-trained actually has been evolved deeply, and in a rich way in medical healthcare, because we are dealing with large amount of data, and sometimes it's unsuitable or improper to design deep learning from scratch. So pre-trained neural networks deals with algorithms, neural networks that are trained previously on data sets, and we can use it again to be applied to our data set. So because of that, it's called transfer learning. Actual transfer learning is frequently employed in deep learning applications, transfer learning is the process of taking a pre-trained deep learning network and fine-tuning it to learn a new task. You see here, we're taking pre-trained deep learning network. Okay, now because most of the beginners in deep learning, okay, can't design a deep learning network from scratch. So sometimes they use pre-trained, okay, and they can understand the parameters, okay, during the process of solving the problem. Now the process of fine-tuning the network through transfer learning proves to be considerably faster and simpler compared to training it from the beginning or from the scratch. Okay, fine-tuning, which means we can update some parameters, okay, to be compatible with our data sets. Okay. The key benefit of transfer learning lies in the fact that the pre-trained network has already acquired a comprehensive set of features that can be effectively applied to various related tasks. Okay, since when we say pre-trained, then the model actually has been trained previously on thousands or millions of data size, and we can use it in a faster way and simpler way to solve our problem. So actually we have two scenarios for pre-trained networks can be used in deep learning for either transfer learning, that is retraining, okay, that is we use the pre-trained to retrain it on small data size, okay, of our problem, or as a template to build a network from scratch by modifying some of its given layers. Sometimes we can update or modify some layers, okay, by adding a layer or deleting of some layers, okay, to adapt our problem or our dataset. So we can use a pre-trained image classification network that has already learned to extract powerful and informative features from natural images to learn a new task. This is the idea. We need to learn a new task, okay, not from scratch, but using pre-trained image classification network. Okay, this this table shows pre-trained networks that can be used for RGB 3D image processing. There are several types of networks, and for example, SqueezeNet, GoogleNet, and most of them they have algorithm and can be coded easily using Python or TensorFlow or MATLAB, whatever, okay, any programming language. And here we have the size of each network, the depth, okay, in terms of the number of neural networks, and the size in terms of the number of parameters. Okay, we have here million of parameters. Okay, and the image input size. Okay, what is the image input size? Based on it, you can, for example, update or modify your data. Okay, to be applicable for each network. And there are actually, for example, ResNet, okay, as a network, has been trained on very images, okay, various images related to, for example, neurons and brain, okay. Now, what is the usage of a previously trained network? There are many reasons, okay, or aspects can be used for pre-trained neural network. For example, for classification, okay, we can apply pre-trained networks directly to classification problems. To classify a new image, use classify function. That's it, simply, okay? And we can use the pre-trained network as is, okay, to our data to classify it. Just for prediction بشكل مباشر. بالمقابل, another usage of pre-trained network is feature extraction. For example, we can use a pre-trained network as a feature extractor by using the layer activations as features, okay, we can use these activations as features to train another machine learning model, such as a supported vector machine. That is, we know that deep learning is automatically can automatically extract features. So we can stop at this step, feature extraction, and later on use the extracted features for any type, any classifier of machine learning techniques, such as supported machine, and whatever. Okay. Another usage is transfer learning. That is, take layers from a network trained on a large data set and fine tune on a new data set. Okay, that's fine tuning, which means just updating or modifying some parameters, in the pre-trained network to handle the new task of our data. Also, we have network modifications. Sometimes we need to modify the pre-trained network, the structure, and treat the modified version as a new network from scratch. When we say transfer, just fine tuning. When we say network modification, then we sometimes modify the version of the network. For example, some layers, or treat the modified version as a new network from scratch sometimes. Now, when can we select between either transfer learning and training from scratch? This table summarize this idea actually in terms of 4 features: training data, computational time, training time, or model accuracy. And usually any designer or any researcher should compromise or make trade-off between, for example, computational time and accuracy. Here, use a pre-trained network for transfer learning, or create a new deep network. In terms of training data, pre-trained network can handle hundreds to thousands of labeled data, which is small compared when you create a new deep learning from scratch. Then we need thousands to millions of labeled data. Remember that in pre-trained, it's already remembered, previously. So small data set is needed for training, while in a new deep network, thousands to millions of labeled data are needed to guarantee we have good performance. In terms of the computational time, the pre-trained usually moderate computation, while a new network compute intensive requires GPU for speed. Here's GPU is optional. In terms of training time, since we have small data size, for pre-trained, then seconds to minutes, is enough to achieve training, while in Scratch deep learning, then days to weeks sometimes are needed for real problems. Now, regarding accuracy, the pre-trained is good, depends on the pre-trained model, while the new deep learning, is high, but can overfit to small data sets. So here we have a problem of overfitting, if we have small data set, which is, we'll return back to the vanishing problem. So in this way, if we need to compromise between accuracy and training data and computational time, then pre-trained sometimes outperforms the new deep network. So if you find a pre-trained network that handles your problem, then you can use it easily and without taking a long of time for training. Now, what are the types of neural networks and their properties? This is actually, this table summarizes the tasks, and what are the corresponding architecture and training data format and network output. Image classification task, the architecture is CNN. Image regression, also CNN. When we say classification, that is, we need to classify either a certain class, okay, for image. For example, if we talk about cancer, we have benign, okay, or severe or moderate, okay, tumor, for example. We talk about image regression, okay, then we talking about some quantitative data that is needed to be inferred from the image. We talk about quantities such as statistical parameters. Then also CNN is applied. In this way, the training data format is image data store, while here we have table, okay, of data, okay, format regarding the statistics. The output is categorical, since we have talked about classification, while in regression we talk about numeric outputs. Object detection, okay, sometimes when we have some important regions are occluding each other, then we applied YOLO, which is I think you look once something like that. I don't remember the YOLO stands for architecture that you only look once, I think. Okay, and training data format is a table, okay, of data, and bounding box, that is to determine the boundaries, okay, of each object that we need to determine, okay, considering that there's occluding, okay, of more than an object and the same inputs. Sequence to label and sequence to sequence, these are using the architectures that have memory, such as LSTM, okay, and the cell array, that data format, and it also to be categorical or categorical vector in case of sequence to sequence. Okay, it will be longer than sequence to label, so it will need categorical vector in this way. For conclusion, I need to ask you another question. Okay, so I'll stop share here and just ask you another question regarding this. Okay, yes, okay. I think I will send you a so please this question. Okay, this one, and please حرروا السؤال من خلال دقائق نشوف. And this question, please, another question. Good. Assume done. Okay. Okay, thank you. Okay, I'll share. Okay, if we see here regarding the second question, what is transfer learning? First choice was training a model from scratch for a specific task. No. Okay, we say that we have trained from scratch and pre-trained. Okay, using pre-trained models to perform similar tasks. Yes, this is the correct answer. Okay, and transforming data between different domains. No, this is not okay our idea. Sharing the model weights with other researchers. No. Okay, and 77%. Okay, لسه عم جاوبه. Okay, done. Okay, فالجواب هو transfer learning هو using pre-trained models to perform similar task, which means, okay, similar task, which means the data are related to this pre-trained network. Regarding the first question, okay, what is the best approach? Okay, the data set consists of remote sensing images. If you see the images in the question, okay, remote sensing, which means, for example, using Google Earth, okay, something like that. Okay, what is the best approach for training a deep learning network? Okay, we have transfer learning or train a network from scratch. transfer learning, okay, which is يعني خلينا نحكي الأغلبية جاوب صح. ليش حكينا transfer learning؟ لما تحكي أنت remote sensing images, okay, for example Google Earth, or for example capturing anything over, okay, remotely, and usually it's built, okay, we have data set, okay, huge data sets, okay, that was used previously to train, okay, network, and usually when you see remote sensing, then transfer learning, okay, is applicable, okay, in these scenarios. حدا عم يسأل أو حدا عم
دكتورة بعد إذنك،
اتفضل.
بالنسبة للسؤال الأول،
مهم.
هلا الترانسفير ليرنينج مش المفروض يكون إنه نستخدم بري ترين موديل لسبيسيفيك تاسك مش سيميلر تاسك؟
لا، سيميلر تاسك مقصود فيها، لاحظ بحكي سيميلر تاسك مقصود فيها، لا مستحيل انا اجيب مثلا صوره دوج واعمل بريدكشن على داتا سيت لمثلا ديزيز معين.
عشان
مقصود فيها نفس البروبلم، سيميلر بروبلم. اوكي
خلص تمام.
اوكي، لما احكي سيميلر تاسك، اوكي احنا لكن حكينا حكينا النيو ايمج او النيو، اوكي، مقصود فيها شيء something نيو، لكن مستحيل انت تعمل بريدكشن. خلينا نحكي مثلا لنبات على داتا سيت او بري ترين نتورك خاصه، مثلا تعمل بريدكشن لديزيز معين مثلا. اوكي، فانت يو شود similar task which means similar problem. اوكي
هو انه احنا يعني انه خلص بندرب هذا الموديل مثلا البري تريند هذا على سبيسيفيك تاسك، يعني هيك مش
لا
المفروض
لحظ،
تكون.
اول واحد لحظ، لا قصدك انت بجاوب ايه؟ training a model from scratch for a specific
هي
task.
جملة صحيحة، هي جواب صحيح، لكن لو كان مثلا سبيسيفيك تاسك بيكون صح.
لا هو انا مقصود مش similar task، مقصود فيها similar task انه يعني مش specific. similar مقصود فيها similar انه اذا كان interpretation هو similar للداتا سيت، اوكي، اللي معمولها ترين على البري ترين نتورك. اوكي
تمام، خلص تمام.
اوكي واضح. similar task or similar problem. okay, we can say. okay طيب، ايش صار اخر شباب؟ طيب turn back للسلايدز هنا. actually the conclusions, okay, of this lecture. Generally, the CNN-based methods for image scene classification can be divided into 3 groups, okay? Either training CNNs from scratch. This is the laser pointer أفضل شيء. Okay, هاي النقطة اللي حكينا أول شيء training CNNs from scratch. Fine tuning pre-trained CNNs on target data sets. Okay, pre-trained CNNs as feature extractors. ماشي. either pre-trained as feature extractors to be used later on for machine learning techniques او انه fine tuning pre-trained. عاده انت بتاخذ انت pre-trained network ما بتاخذها as is، اوكي، الا اذا كان شيء عندك so simple الداتا اللي عندك وانت يعني لاحظ انه similar اوكي بالبروبلم اللي عندك. but usually when we deal with complex problems you need to fine tuning the parameters of the pre-trained CNN or training CNN from scratch. This is simply applied when the pre-trained network is not available for your problem. Okay. A pre-trained model in the training helps in lowering the training time and generalization error. Okay. And in medical tasks, CNNs are commonly combined with other neural architectures, okay, such as recurrent for sequential data and transformers for pattern recognition to enhance their applicability and effectiveness in complex medical data analysis. Yes. So I'm done. Okay. بس إنه to show you إنه this lecture okay بصراحة أخذتها من different books، يعني حتى يعني كتب حديثة في مجال deep learning، فيها deep learning for data analytics foundation okay biomedical applications and challenges in 2020 published by Elsevier. وفي كتاب اسمه Machine and Deep Learning using MATLAB Algorithms and Tools for Scientists and Engineers okay by Wiley and this year published. وفي كتاب اسمه Deep Learning a Visual Approach okay in 2021. These are خلينا نحكي the main sources okay of this workshop. And thank you for listening. Now يعني هلا أتوقع وقت كافي إذا حدا يسأل السؤال. Okay, I think. بس في حدا رفع إيده.